Good evening, all of you. Anyway, I just introduce few things. Why CPUS is interested in the so-called advanced James Webb Telescope. In science, telescope is a big metaphor, as well a good tool, great tool in fact. During the moment of Galileo, Church was objected his invention in a way. Church or through religion, people are interested, so-called moksha, so-called heaven, reaching of heaven. They were just metaphorically thought that science could reach easily than the religion, so-called whatever they called heaven or moksha in a way. But soon after that, the Galileo's tool has become a big metaphor as well a great tool for the all development of sciences. During that time, that invention of telescope and later developments have led to various things, and perhaps now the most advanced tool is this James Webb Telescope. Anyway, I will not tell the details of those things which Dr. Girish will share with you. And as a organizer of this webinar from the Institute of Center for Public Understanding of Science, I just wish to share a few things. In public understanding of science, a lot of things are generally not discussed with public. However, we are interested in taking any issues, even the so-called much discussed, much less discussed issues are also to reach the public. At least we are interested in making things known possible to the public in their language. In their language means maybe in Kannada or maybe in public language kind of issues. Because any development of science is generally with the help of public money. And so true with any development, so true with any invention, so true with any research per se. So I am very happy, at least something around 30 plus people have joined today, and I welcome all of them. Kindly maintain the protocol of webinar protocol that you mute your audio as well video. And interestingly, today the webinar presenter, the scientist is Dr. Girish. Today morning when we met him, he has assured that any participants interested in any branch, any interesting questions related to astronomy can be discussed apart from the James Webb Telescope. So that way, we have an additional input apart from what we have claimed so far. So personally, I thank Dr. Girish in that respect. And however, his details, Akash will be sharing it later. I will not talk about Dr. Girish and his institute, which you know already anyway. So, other way, as a institute, that Public Understanding Institute, why the so-called advanced development should reach? Because the simple thing, last December, this has been in news. That is something like very advanced telescope has been. What will it happen? What is the content? So such curiosities are generally with public. Such curiosities are generally with anybody. I mean, even majority of the scientists also may not know many things about other branch of knowledge systems which are not different from. So in that way, we are interested in making people possible to look at the other things which are not totally aware of or which are not they are specialized in. So that way, this small effort perhaps will help our readers, will help our viewers, will help our people who are associated with Center for Public Understanding of Science to know some minimum things of what is happening in science. So likewise, this particular website, this particular development of telescope, which is in fact one of the most interesting tools developed so far after the Hubble, and now that is taken a very prime position far from Earth, say around 1.5 million kilometers away it has been placed, and that itself is a wonder. And beyond that, what is it? How does it matter? How does it? All those things perhaps Girish will share with us. And I am very happy, including me, when all of us will get to know what is the reality of the issues and how it will going to make our dreams possible. So I'm that way. Anyway, I'll just welcome all of you and thank you for joining us. And I hope you will enjoy the words of Girish and his knowledge. And kindly, if you have any doubts other than the telescope issues, generally with respect to any astronomy issues, you can just talk to him. You can raise your things. Girish will be very pleased to respond to you. So I hope with this I'll just conclude welcoming all, and I'll leave the floor to Akash to make things further. Thank you, Akash. Please proceed.
Thank you, Dr. Channesh. Once again, I welcome all the participants and today's speaker, Dr. V. Girish, on behalf of Center for Public Understanding of Science. Now it is my immense pleasure to introduce Dr. V. Girish to this gathering. Dr. V. Girish is from Gauri Bidunuru. He completed his Bachelor of Science, BSc from National College, which has a very rich legacy in the history of Karnataka. Then he completed his MSc in physics from the Bangalore University in the year 1998 and then joined Indian Institute of Science, also called as Tata Institute, to pursue his PhD. He completed his PhD in the year 2005 in the subject called Rapidly Oscillating AP Stars. He was awarded PhD for this topic. Then he did his postdoctoral fellowship at Tata Institute of Fundamental Research, Bombay, and worked on X-ray studies of cataclysmic variables. He joined Indian Space Research Organization, ISRO, in the year 2006, and he worked in ISRO Satellite Center. Now it is called as URO Satellite Center for a couple of years, and now currently he is Associate Director in ISRO's Satellite Space Science Program Office in ISRO Headquarters, Bengaluru. This is a brief introduction. As Sir has previously informed all of you, he is a very keen researcher in the field of astronomy. So, without further delay, I leave the floor to Dr. V. Girish to enlighten us with regard to James Webb Telescope and also the field of astronomy. Over to you, sir.
Thank you, Akash. Thank you very much for those kind words. And before I start my presentation, I would like to thank Dr. Channesh and Center for Understanding of Science for giving me the privilege of talking to you in front of you. So, what is James Webb Space Telescope? So, currently, so the understanding is like it is one of the major or most important science marvel or engineering marvel ever achieved or attempted by humans. Okay, so but it looks like very small. So what are the important things and what we are going to achieve by sending James Webb to space? So I'll be talking about these things. So if you have any doubt in between, as Akash said, I don't know how the procedure here. Either Akash, you can actually correct me. Either you can raise your hand and I take the question.
Sir, after your talk, there will be QA session, so people can ask the questions, or even they can type their question in the chat box.
Great.
So you can take up the questions later, sir. Just to not to interrupt the flow, we are following this protocol.
Sure. Thank you. So let me start with before going to James Webb Telescope, I should actually talk about Hubble Space Telescope. Okay. So And Hubble Space Telescope, many people say that James Webb Space Telescope, or from now onwards, I might be interchangingly calling it as either Webb Telescope or James Webb or simply Webb. Okay, so this is people say that as a follow-up mission for Hubble Space Telescope. I am sure almost all of you will be aware of Hubble Space Telescope. It has just completed 30 years of existence in space, and it is still providing fantastic results. Okay, so without actually going through Hubble Space Telescope, it's almost impossible to talk about James Webb Space Telescope. But JWST or James Webb Space Telescope, whatever we call, so in my opinion, it's not a uh, follow-up mission for the Hubble, but it's going to be a complementary mission. I'll come to that later in the presentation. Before that, why do we actually need a telescope? Let's see. So how many of you know how many stars are visible to our naked eye? So in Bangalore, if any of you are from Bangalore, how many stars you see in an eye? Usually it's not more than few hundred stars because the background light is very, very high in Bangalore. But if you just go around 20 to 30 kilometers away from Bangalore and go to a village and allow your eye to get used to the darkness, and if you see the sky, you will see anywhere around 2,500 to 2,600 stars uh, in the sky. And if you have a very good eye, to be frank, the overall in the whole world, whole universe, what our eye can see is around 10,000 stars, 9,956 to be precise. Sorry for the typo. So these are the total number of stars you can see, assuming that you are in a very, very dark place and your eyesight is very, very good and you don't have any other problem and you have got used to adjust it to the dark. So, but this will increase. Okay, do you know what this is? This is what we all of us know as um, Big Dipper, or in Kannada or in our Hindu mythology, we call it as Saptarshi Mandala. These are the Saptarshi Mandalas marked by their name. So you know that in most of our Hindu marriages, they actually take you and show Arundhati star. You know the Arundhati star has a significance in astronomy. This Vasishta, whatever is there in this one, this Vasishta, or in English what we call as Mizar, is not a single star. It's actually a binary star. Means it's two stars revolving around each of them as a husband and wife. So the major one is called as Vasishta, and the smaller one is a fainter one is called as Arundhati. And Arundhati happens to be at the extreme end of what our eye can see. See, our Purvajaru means our ancestors knew about the importance of this. So that's why they used to show Arundhati to the newly married. If a person spot Arundhati, means that they have a fantastic eyesight, 20/20 eyesight. So this is the easiest way, not going to an ophthalmologist or any other doctor. So you can say whether their eyesight is correct or not. So good, na? So this is if you can see this Arundhati, that means that you can see around 2,500 stars in the sky at that time. But you just use a binocular. So binocular with 50 mm aperture, then this number will go up significantly or exponentially. You can see up to 2,17,000 stars. I told you Arundhati is sixth magnitude star, and the faintest you can see with a 2-inch binocular in the same spot will go up to some 2,17,000 stars. So the difference between these three magnitude corresponds to 2 to the power of 2.5 to the power of 3. It's around some 20 times more, but it's not the 20 times. You see, the number of stars are increasing. Assume you are having a bigger telescope, say a 15-inch telescope. When I say 15-inch telescope, the mirror or the lens of the telescope is 15-inch. So then you can see 380 million stars and you can reach up to 16th magnitude. So the difference between of 5 magnitudes give you a intensity or the brightness variation of around 100. So just with a brightness variation of 9 to 16 is 7 magnitudes, that is a little more than 100, and that increases the number to 380 million stars. And Yeah, our Milky Way, you know, this Akashaganga or Kshirapatha or our own Milky Way, it has around 300 billion stars. So to see these 300 billion stars, we have to go larger and larger telescope. So with the larger and larger telescope, you can see fainter and fainter objects, and hence you can see more and more of them. So then, just for the completeness, because I'm talking about James Webb Telescope, so there are mainly two types of telescopes. One is refractive and another one is reflective. The refractive one uses a lens, to what we normally see in a magnifying lens, or a reflective one is a mirror. So not a curved mirror, so that the light is reflected back. In astronomy, we do not use telescopes for magnification. So magnification is just a number for us, but the telescopes are always used as buckets to gather photons. You know that when it is raining, if you keep two buckets with a different diameter, you can collect more rain with one with a larger diameter, right? Exactly like that, by collecting more and more photons from for the fainter and fainter stars, so we can see farther and farther into time. I'll talk about that later. Okay. So the problem with the refractive or the lens is the lens has to be supported only at the edges, because if you support it from the back, then it will cut down on the incoming light. So you will lose light. See, you are going to larger and larger size of a lens just to make sure that you can collect more. But then what's the use if you actually cut off them and make it smaller again? So this is the reason why the highest or the largest lens-based telescope is only 40 inches. Okay, so if you want to go to a little more than 1 meter, then you have no other option to go for reflective mirror. Okay, now reflective mirror has other problems. See, now can you see this figure? What is happening is, here we are using a reflective mirror. Mirror means it's not a flat mirror, it's a concave mirror, parabolic mirror. So the light from here will be reflected here and goes here. Now there is a problem. Earlier, if it's a lens, the light comes like this and goes here and you can see here. But now it is reflecting back. Where will you see? That's the problem. Then that was corrected by two people. One is Newton. He put a mirror, okay, plain mirror on the way, so that whatever the light getting here reflected back, it goes to eyepiece. Okay, so here you can see in this one, the light falls here, gets reflected from the lens, mirror, and comes here and gets reflected here, and you can see from here. But this will be okay if you are using it only for observing stars with a smaller telescope. If you want to actually use it for a scientific purpose, where the scientific instruments will be very, very heavy, then managing this or balancing this will become very, very tough. That's why there is another way of using this. So you make a hole in the middle of the mirror, so that light from the mirror gets reflected by a secondary mirror and comes through, and now you can keep all the detectors and everything in the back side. Now, since it's almost at the symmetric end, so balancing this will not be that tough. This is called as Cassegrain. Okay. So then comes to mount. So you know that Earth is rotating, okay, on its own axis. 24 hours it goes make one round. So it almost, because of this, the sky looks like it is moving. So then whatever the stars which you have in the field of view, they will move away after some time. So how do you correct that? So you also have to move the telescope along with that, what we call as tracking. So when you do the tracking, then it is one way of tracking is keep one angle fixed at the tilt of Earth, that is around 17 degrees. If you do that, then you have to use only one motor to move this. So if you move it with a constant velocity, it will compensate for the rotation of the Earth. Okay, but then this is cumbersome. You have to have a motor and everything. Another one is alt-azimuth mount, where you have the option of rotating in two directions, altitude and azimuth. Okay, these are the overall picture of whatever telescope is. So anything is, this is a very, very brief introduction because it's not the major talk of this one. So I'll just stop it here about telescope. So you know that telescope, when you're seeing through this, our eye can actually integrate only for 1/25th of a second. So that's how we all have movies. So in the movies, what they do is they move the pictures so fast, more than 1/25th of a second, so that it looks like they are moving. Even though individually each photo is a separate individual static photo, but because it's moving with a very high speed, higher than what our eye can actually take a photo, so it will act like a moving picture. So that means that whatever the light we are seeing can be integrated only for 1/25th of a second. But the invention of detectors, initially photographic plate and later on cameras, now CCD cameras, etc., has actually overcome this. So what is happening now is you can integrate it for hours together and in some places days together. So if you have one star which is giving out only 1 photon per second, so then by the time your eye blinks, that photon wouldn't have even reached your eye. So you can never see that star. But if you integrate, if you keep on observing that star for say 10 minutes, then in 10 minutes you will get 600 photons. So that's a very good number in astronomy. So that means that you could see a fainter star which would never be seen by our eye. So using these two concepts, one is telescope, which is much bigger than our eye pupil, which is maximum 8 mm. And now this telescope size is almost like 10 to 30 meters, etc. And at the same time, instead of 1/25th of a second, you can actually integrate it longer and longer, so you can see fainter and fainter. So these two combination has given fantastic, wonderful pictures. So most of these pictures are taken from Hubble Space Telescope, just for comparison. So these are all called as Planetary Nebula, which is formed by the explosion of a star, end state of a star. Okay, I'm not going to in details of that. So this is called as a nebula, where this is just a dust and other things. These are the places where the stars are getting born. These are the nurseries of stars. And this is a tadpole galaxy. You can see that the galaxy is getting extended. This is because it is getting merged with another one. So like these kind of brilliant pictures are is possible with the help of telescope and detector. Okay. So now the question is, since the size, so this is gives the comparison of sizes of all the telescopes currently in on Earth or in space or planned for future. Now you can see that Hubble Space Telescope with the 2.4 meters lies here. Compared to that, there are much bigger telescopes everywhere. For example, 100-inch Mount Wilson or Hale, 200-inch Mount Palomar. You can even see this. There are a Keck telescope which is 8 meters each. There are 2 of them, and so now India is also part of this telescope called as 30-meter telescope. Now you can see that some of them looks like one single one. Others are called looks like segmented. The reason is, as and when you go, see mirrors, even the mirrors or lenses, everything is made out of glass. So glass is very tough to actually grind, give shape, because it has to have a perfect shape. And then at the same time, also take up, it will get stressed. So when you actually push it like in an angle 90 degrees to the horizon, then automatically there will be a lot of stress because the weight is very high. So to avoid this, what the people started using is, and when you are making anything in glass, the rule of thumb is, so for the stability, it has to have at least 20% of the size. Means if you have a 1 meter mirror, then the thickness of the mirror should be at least 20 centimeters. So that actually says that if it is, if I'm planning to make 8 meters, then the thickness should be around 1.5 meters. That you can imagine the weight of that. Okay, so that weight, how do you move, and how do you balance it, and how do you actually remove all the stresses? So all these problems comes into picture. That's why what nowadays people you do is, when you talk about larger and larger telescope, instead of going for a single monolithic mirror like this, you split it, make smaller and smaller telescope mirrors, and combine them to form a single mirror. This is what is even James Webb uses. I will talk about that later. Now, this is a 30-meter telescope by this one international team of astronomers, and India is also part of that. Each of these small segments, like honeycomb segment, whatever you see, that itself is around 1.4 meters. Indian Institute of Astrophysics, that is in Bangalore, is making some of these mirrors. Okay, and we are expecting a European extremely large telescope, which might come later part of 2030 and more. And this is a just comparison. If this is a tennis court, James Webb mirror is 8 meters, but overall James Webb telescope will be as big as a tennis court. Okay, just keep this in mind. I'll mention that later in the day. And just for comparison, the world's largest telescope, that is a radio telescope, Arecibo, is a part of that is shown here in the border. But unfortunately, we lost it some few months back because it just collapsed on its own. Now it no more exists. Now, so you can see here that Hubble is this size and James Webb is so big, but what we are planning is 30 meters. So then why do we actually go to space by spending almost 100 times more money than whatever we can do achieve the same on ground? The reason is this. So you all know, or you have all sung this Twinkle Twinkle Little Star, how I wonder how. So you know, right? So this is the twinkling. What is happening is Earth's atmosphere actually moves the light around. So that means that the light will not fall at one place. So this is why you sing the song Twinkle Twinkle Little Star. But for astronomers, it's a bane. So because of this, what happens is it gets blurred. Okay. So because it will not be in focus, one photon which is coming from this direction will fall next time here, next time here. So they'll be dancing around. See the same thing. What happens if you go to upper atmosphere, beyond atmosphere, that is beyond around 102 kilometers above. So Hubble has given the same photo. See the difference. How much clarity you can get just by going above the atmosphere. And second thing is the background noise. I told you that from Bangalore you can see very, very less number of stars. That's because the background itself is very high. So in front of that background, you have to pick a star which is as faint as the background. So the same star, see how bright it looks in space because the background is almost completely dark. Whereas on Earth, it looks like this. But if you come to Bangalore, it is almost impossible to even pick. So these are the few reasons why we are forced to go to space. In addition to this, I forgot to mention one more. Certain wavelengths are not allowed through atmosphere. Lucky us. For example, you all know that X-rays can cause cancer, UV can cause cancer. Because this atmosphere stops most of these wavelengths, so we are saved from cancer. But as an astronomer, I am very unlucky because I can't see these wavelengths from ground. The only way I can see that is by going to space. Okay, this is till now it is about just an introduction. What is the telescope? Why do we need a telescope? And why we need to go to space with a telescope? Okay, I hope you got some idea. Now I'll come to JWST. As I mentioned, without mentioning about Hubble, you cannot talk anything about JWST. This gives you some approximate numbers. Hubble was launched 32 years back, whereas JWST was launched last year on Christmas. Hubble, it's a 2.4 meter telescope. 2.4 meter is the aperture of the telescope. It weighs 11.1 tons, whereas JWST is 8 meters. Okay, that is almost 4 times or 16 times more effective area, but it is half of Hubble. See the marvel. See, this is one of the marvel achievement. And Hubble was 13.2 meters by 4.2 meters. This is JWST is 20.2 meters by 4.2 meters. This has a problem. Sorry, I mentioned the 8 meters for JWST. It is 6.5 meters. So in front of JWST, Hubble looks like this. Okay, but even though the size is almost this bigger than Hubble, the weight is half of Hubble. And Hubble works in visible mainly, whereas JWST is going to work in infrared. Okay, so the plan of my talk is I'll start with an introduction. I'll pick some major challenges involved, and I'll talk about some science. I'll end with what are the science expected from Hubble. Hubble is renamed as James Webb. The James Webb is an NASA administrator who is responsible for Apollo landing and sending man to moon. Okay. So Apollo has subsystems. We call it as whenever we talk about a satellite or something, we divide that satellite into multiple parts, and which we call it a subsystem. One is the integrated science instrument module, which will carry all the science experiments. Optical telescope element, which is the basic optics, which consists of mirror and secondary mirror and everything. And combined to the optical telescope plus this integrated science instrument module, combined together as one major subsystem, and sun shield. Sun shield is a major engineering challenge for Hubble, JWST. So this I already mentioned. If we have made JWST the same way Hubble was made, then the weight would have been made it too heavy for liftoff. So the amount of fuel we don't have launcher or a rocket to carry. If JWST is made exactly like Hubble, just to give an example, Hubble is around 11 tons. So 16 times that. So we are talking about almost like 200 tons. So we don't have any. And when I say we, entire world do not have any launcher which can carry that. Okay, and at the same time, whatever the rocket we chosen to carry this, it has a fairing, means on the top to survive from the heat generated by friction, it is covered by something called a fairing. Okay, so it will not fit into that because the size of the fairing is very, very small, 5.5 meters. So because of that, it has to be folded. JWST has to be folded. That was another challenge. So this gives an idea of how big JWST is. So this is a one-to-one model of JWST. You can see that this big one is the heat shield. So I'll tell you about why this kind of heat shield is required. And this is a telescope. So many people involved in making this telescope, and this is almost the size of a tennis ground. Okay. So as I mentioned earlier, JWST is made out of individual small mirror segments. Each one is around 1.4 meters. And to reduce the weight, instead of normal glass, $0 or anything, it was made with beryllium. So each of this 1.4 meter mirror is only 20 kgs. Okay, this is made with hexagonal shape because instead of hexagonal, if you make it as a circular, you can see that there will be gaps. So you will lose out on that. So to cover that, it is made with hexagonal. And because it's made with hexagonal, you don't have to make each one with a different figure. So there were only 3 major ways of making figures was required. So that means that their design was only 3 instead of 18 numbers, 18 different designs. So it was easy to make or replicate. So this is segmented and controllable. Controllable means this mirror has to have a shape. Hubble, when it was designed such that if something goes wrong, so scientists can go on another rocket and repair it. But JWST is going to be in the Lagrangian point. I'll talk about Lagrangian point, which is almost 5 times longer than a higher distance than our moon. Okay, so it is not possible for anybody to go there, repair it, and come back. So that's why it has to be designed such that if something goes wrong, we should be able to take it. So that's why what they have done is, this is as I said, this is thin mirror. So behind that we have actuators. Actuators is nothing but ones which pushes and pulls so that it modifies the shape. So by modifying the shape in such a way that instead of plane, we can make it this bent or make it curve, so that when I put it next to other, these two will act like a single parabolic mirror, right? A plane can become a single parabolic, but I am exaggerating. The variation will be in microns, but that is the one which we require. So this is how they were actually set together. and the actuators will move it up and down so that overall it looks like a single mirror. And you see this gold. The problem with beryllium is beryllium cannot reflect infrared radiation. It simply absorbs. So to avoid that, each mirror is plated with gold, but not too much of a gold. This 1.4 meter individual mirror is plated with only just 3 grams of gold. The thickness of this gold coating is very, very small. That is around 50 nanometers. So overall, for all the 18 mirrors, the total amount of gold utilized is very, very small. That is around 50 grams only, as heavy as a golf ball. Okay, so Ariane 5 fairing is 4.7 meters by height, 17 meters, but JWST is 8 meter height and 21 meter by 14 meter. We cannot push this into this size, so that's why it has to be folded. So this is the size of that. So these two will get folded. See, this entire thing will be folded to this. Okay, so that this can fit into the fairing of the rocket. So this is how the folding works. Okay, so after folding and it is fitted, then in the beginning I told that JWST is something similar to Cassegrain focus. So that means that the light from the mirrors are reflected back, and the reflected back is falls on a secondary mirror which is around 0.74 meters, and which is kept at 8 meters, that is 24 feet away from the JWST. That's another problem. How do you keep something 24 feet away, whereas you're talking about entire rocket fairing is around 11 meters. Now, for this reason, even this has to be folded. See, here is the picture. This secondary is kept here. Okay, and it cannot go like this in the launch. So this also has to be folded. So how does the folding happen? The one fold is the mirror itself, and the another one is the secondary mirror. See, this has to happen in space without anybody doing anything. Okay, and even some few micron error here and there will lose entire thing because your focus will be off. In space astronomy, we hate anything which moves because anything which moves can go wrong anytime. So, or it might even happen that it might just get stuck. It will not open. If that's the case, entire mission is lost. So that's why we do not like having any movable parts. But JWST couldn't do away with any of these without any movable parts. So that there lies several challenges. Okay. In addition to secondary mirror, it also has a tertiary mirror and primary mirror. I'll not go into that in detail. So the light from a star falls onto the main mirror and gets reflected into a secondary mirror and goes to a tertiary mirror kept behind here, where it gets split into all the 4 instruments. Okay, so that is one part of optics. Second part is the thermal management, means the temperature. I told you JWST operates in infrared. The problem with infrared is you might see that anything which is at a higher temperature, around the temperature, even you yourself, you might have seen for COVID, how do the people check your temperature? They simply put a gun at you, and which measures the infrared radiation from your body, right? So this infrared radiation can spam, means it can saturate all JWST mirrors, different sensors, detectors. So unless and until you cool your body such that it becomes very cold, so no emission comes out of that. I told you, if you have a temperature of 102, immediately the gun will catch. So the difference between only that, right? That means that photons it is measuring. Similarly, the whole telescope has to be cooled minus 230 degrees below zero. So at 0 degrees, the water becomes ice. Okay, that itself is very, very cold. If we go below 40 below this one, hydrogen will start becoming liquid. At 140 to 160 Kelvin, sorry, 160 minus 160 degree, so helium will start cool. So like this, nitrogen cooling and everything. So you might have seen I don't know how many people have seen Terminator 2, where liquid nitrogen, in the end, the Terminator will fall in the liquid nitrogen and he just breaks. So we are talking about temperature much, much below that. So the instrument has to survive that temperature, cold temperature, and the instrument has to work in that cold temperature. For example, if anything, a moving part is there, you have to use a grease or oil to make sure that the friction is less. But now at that temperature, that will freeze. That will become like ice, solidifies. So it will become like a gum instead of making a free movement, right? So these are all the problems. And more than that, Sun is actually dumping energy continuously on the telescope. Now, how do we stop this? Okay, so these are the things which needs to be taken care in JWST. That's why I'm putting that as a separate entry here. So in 3 ways, the temperature is actually reduced. One is by choosing a proper orbit. Second one is passive, and the third one is active. Okay, so before going to go where exactly JWST is going to be, I will talk about Lagrangian points. So Lagrangian points are just a point where the gravity because of one cancels out because of gravity because of the other, or centrifugal and centripetal forces of the other. So if you come here, there will not be any force of attraction between here and here, L1. That is called as Lagrangian 1. Our Aditya mission, which is going to be launched sometime in this year, is going to go here because it needs to keep on looking at sun continuously. By keeping here, so it will be looking at sun 24 hours a day. Okay. Then the second one is behind Earth, is called as Lagrangian point 2. This is where JWST is going to go, and this is where some other more telescopes are already there. For example, Spitzer is one of them. Spitzer is also an IR telescope. Okay. Then there are two more called L4 and L5. We scientists have not found any use for L3. The reason is because sun is going to be in front of us all the time. If you are somebody goes to L3, and you know that if you have Tata Sky, you might have sometimes seen that around 12 o'clock noon, sometimes you might see the error message saying that, so because sun is also in the same field of view, the emission from satellite will be completely stamped or saturated by emission from sun. Sun is a very, very high emitter of radio and other waves. So that means that you cannot have any contact with L3 directly. So scientists have not found out any use for here. But L4 and L5 are the most stable points, and many of these asteroids lost from others comes and stays here. These are called as Trojan asteroids, and these two have found observations for sun. So assume that if you are here, then whatever is coming from sun first reaches here and then Earth, so that you have some time to know in advance what is happening. Okay. Recently, you might have heard that Elon Musk lost almost 25 satellites because of a flare, right? So that flare information can be obtained in advance if there is another telescope here. Okay. So, but being here, so now most of this light, it's like eclipse. Most of this light from sun is blocked by Earth, so that less heat reaches here. So that's one way of saving yourself from sun rays. So that is very, very much necessary, and everything here is dark, so that you will have enough observations. You cannot look at sun, but you cannot look away from sun all the time. So whatever it is coming beyond that will be shaded by this heat shield. Okay. So how does the heat shield work? So the heat at this one end of the heat shield, the temperatures can go up to 383 degrees or above, whereas nominally it is around 83 degrees centigrade. But at the other end of the heat shield, the temperature will be cooled to minus, means but just by not allowing any light to pass through up to here, the temperature reduces to minus 233 degrees centigrade or 40 Kelvin, which is more than enough for all the three instruments on board JWST. Okay, these are made from very thin layers of krypton. Okay, but because krypton is very, very stable, it will not wrinkle or melt or do anything up to 400 degrees centigrade, and it can retain its stability up to minus 269 degrees centigrade. But to increase the reflectivity of sun, whatever the solar photons, so it is coated with aluminum. So aluminum, that is silver color, whatever you see, or in the mirror also we actually coat aluminum in the backside because to increase the reflectivity. So because of this, 90% of the photons are just reflected back. So they will not contribute anything for the heat. And the two of them facing these two, which is going to face the sun, are again doped with silicon to increase the reflectivity, so that the reflectivity is maximum and it will not allow anything inside. But you know that you see that these are all very, very thin sheets. Okay, these thin sheets are so thin that if you might have seen, if you actually use a balloon, then if something actually, if you take a small pin or something, you just move it, instead of just making it as a hole, it simply ruptures. So it means that whatever the small hole happens, that can actually keep on spreading. Now, what happens if like this happens? Because this is a thin sheet, then it will get a tear by any meteorite or anything. The tear will continue and it will destroy the entire sheet. So to stop that, what they have done is they have used steel, very thin steel tapes. So you can see these lines, so that it will stop the tear. So if any tear happens here, the tear will be stopped up to here. It will not spread throughout. So that only small portion is gone, but other things will retain. At the same time, you see that this is a very thin sheet. When you take a thin sheet and try to stretch it, it will become like smaller here and this one, right? So to stop that, in the edges they have made actually some designs, so some pressing, forming, so that this, even if you stretch, the whole will maintain the shape. Okay, so this shows the release mechanism. Oh, it's already time. So I'll just rush through this because I do have some science to see. So this is how the film or the heat shield gets deployed in space. See, so many hundreds of people working on this to see the deployment, but this has to happen on in space without any intervention and automatically. Very small, a small stop anywhere will destroy entire thing. Once all the 5 layers are stretched and to reaches its text shape, then in between them, again stretch will be gap, so that heat from one by touch or this transmission should not go reach the other layer. See the gaps there? Now you know the size of this heat shield. See, 75% of single point failure in JWST is just in this one mechanism. There is a possibility of almost like 1,300 things going wrong in this. Even one of them had not performed properly, then entire JWST would have been gone. Okay, so this is the kind of things which it has to do. Now, because of this, the temperature at the JWST, actually the mirror is 40 Kelvin, whereas the sunlight is around 350 Kelvin. Okay, but this is not enough for mid-infrared instrument, which needs to work at 7 Kelvin. So for that only, they have actually made a dedicated mid-infrared detectors, cool this. So, and also, when you do anything cooling or when there is any mechanism, when any moving part, there will be vibration. This vibration, very, very minute vibration, can actually cause the telescope to move away. So there will be jitter. So it will not focus properly. Then we lose everything. For that reason, this was specifically designed and developed with the two opposing motors, so that the motion of jitter with this cooler is very, very minimal. And also it uses a helium as a refrigerant gas, and the final temperature reached after using this is 6.2 Kelvin. You know the funny thing? The heat is transferred, the hotter from the hot position, the heat is transferred to the colder area using sound waves. Can you think of like sound itself carrying away energy? So that's the first time it was attempted. So I'll just say that there are 4 cameras in JWST. So all of them use a similar detector, but with different doping. I hope that when you reach high school or college, when you are talking about transistors, PN junction, NPN junction, you will understand what is doping and what is the other detectors. Okay, I'll not go into that detail. Okay, so and one of the major goals of these instruments is to look for planets around stars. But what happens? Planets do not have its own light, so they will look very, very faint. Whatever they can give away is the reflected light from the star itself. But star will be millions and millions of times more brighter than the planet. So if I keep something like, if you see in the morning, assume that in the daylight, if you just light a lamp outside, can you see the light from the lamp, that the candle? It's very, very tough, right? So to see the light from candle, what you have to do is you have to stop the light from sun. So the same way, the center portion of that particular camera is covered so that the star's light will not reach here, so that only you can see the planetary structure, disk and others. Another one is spectrograph. It takes a spectrum. You might have seen when you see solar, this one with your, you can actually create a spectrograph at home easily with a CD. Just use the CD, you will see that the light will be split into multiple colors. This is just a spectra. But the problem is, if there are multiple stars close by, the spectra will overlap, and then you cannot actually say whether the spectrum is from this star or this star. So to do this away, what they have done is, they have made a multi-object spectroscopic with microshutter, whereas the brighter ones will be switched off. Means, so the light from that will simply go in like this. So this light will not contribute to here, so that you can actually do one closer to. So I'll just skip all these things. Okay, we'll go to science from JWST. Okay, so one of the major use of JWST is as a time machine. Now you can ask me, what is a time machine? How do you actually call? Why do you and how can you tell that it's a time machine? Nobody can go back in time with using JWST. Yes, I agree. But all of us know that light travels with a fixed time. For example, you take a bus from here to Mysore, Bangalore to Mysore. Everybody knows that because Bangalore to Mysore is around 150 kilometers, and with a gap, with a stopover for a coffee or tea, so we need 2 hours to reach there. Okay, you take any vehicle or anything, you cannot reach there before 1 hour, right? Even if you take a higher, if you ask all the roads to be closed so that only your vehicle is allowed and you are moving at 100 kilometers, even then you need 1 hour, 15 minutes to reach Mysore. That means to say that whatever the speed you go, the distance takes some time, right? Exactly like that, the light also travels with a fixed speed, that is 3 lakh kilometers per second. Now, from sun to us, the distance is such that if I go, if I ask someone to switch on a light or I put a switch on a torch from sun, it will not be visible to me immediately. So it will take 500 seconds to reach me. So that means that whatever I am seeing sun now is actually sun how he was 500 seconds away. So you extend the same. The nearest star, Proxima Centauri, is 4 light years away. That means that the light from Proxima Centauri took 4 years to reach us. That means that if I'm seeing Proxima Centauri now, what I'm seeing actually is the Proxima Centauri how it was 4 years ago. It is 4 years time. We have our all the other things. Sun is 10 kiloparsec away from center of the galaxy. 1 parsec is 3 light years. Kiloparsec is 1,000 light years. So 3,000 light years. That means that we are seeing, if we see at the center of the galaxy, if we can see, then that means that we will be seeing the galaxy 30,000 years away. So extending like that, there are galaxies which are million light years away, and some of them are billion light years away. That means that when I'm seeing a star or a galaxy 1 billion light year away, so now that means that I am seeing a galaxy which was how it was 1 billion year away back, right? So in that way, we are going in time. So that's what is meant by time mission. Okay. So Hubble has observed galaxies billions of light years away, and JWST with its increased sensitivity look very, very further than 13.6 billion light years away. So very close to the Big Bang. So this is very, very small patch of sky. So 1/10 the size of our moon, that is a patch of the sky. But in this one, there are almost like 10,000 galaxies. So the fainter ones are very, very far off, brighter ones are close to us, and some of them are irregular, etc. So each dot is a galaxy. So our Milky Way, which is having 300 billion stars. Imagine. So a small portion has 10,000 galaxies, but with the JWST, this number will be increased to hundreds. So we can see almost million galaxies in the same area. Okay, so then you can imagine how much more farther away we can see, and how it works as a time machine. So this is so close that we are expecting to see light which started in the first light that was started after Big Bang. Okay, and then when the galaxies were formed very, very initially, not now. And life cycle of stars, whether stars are born, how do they get born, how do they live their life, how do they die, etc. And then exoplanets means, so almost everybody, including me, wants to know, are we alone in the universe? When I say are, I'm now using plural R for me. Are we alone? Means we are not alone, right? We are not alone because I know I have so many people in Bangalore, sir, but I'm not talking about it. Other than Earth, is there life anywhere other than Earth? And then push that further and say that, is there any intelligent life anywhere else other than Earth? See, I told you, our Milky Way galaxy has 300 billion stars. Okay, assume that 1 in a million chance, even 1 in a million has a planet. So then that is, our Milky Way itself has around 300,000 stars. That is stars with planets. Even if there is 1 in a chance of 1 in a million life, then in the Milky Way itself there should be planets with hundreds of planets with life. Yes or no? And we are talking about tens and tens of thousands of galaxies. Okay, so why should we think that we are so special that Earth is the only place where there is life? Okay, what is first light from the end of epoch of realization? So I'll try to make it as simple as possible. So the scientists assume that our universe started with the Big Bang. Okay, when the Big Bang happened, there was only energy everywhere. Okay, initially it was only gas, and this gas and the hydrogen, electron, and others were formed. And when it was only hydrogen, but because of the very high temperature, this was all ionized. So whatever the rays which was there, so only the energy was given out. This energy reached everywhere, and because as photons move in space, they lose energy because you have to do some work to do some. You have to have energy to do some work, right? So continuously losing this. Now we see everywhere as cosmic microwave background. You might have heard of 2.7 Kelvin cosmic microwave background. Then around 300,000 years, the universe began expanding, at the same time getting cooled. When it started cooling, the ionization, whatever the electrons and hydrogen atoms came together, and they formed neutral atoms. Okay, so around 400 million light years from the Big Bang, these atoms started coming closer and closer. When the two of them comes closer, their gravity will be more than one single atom, so it will attract the third one. So because now it is 3, it will attract 2 more. So like that, it will keep on growing and growing and growing. When they start growing, to conserve the angular momentum, at the same time it will start spinning also. So you know that when it becomes a lump of mass, the center, when you see that the temperature will keep on increase at the center, and at the same time the temperature pressure will also increase. So at one point, so this temperature and pressure reaches to such a level that there is a possibility of fusion occurring. So it will we say that there are stars are born. So these are very, very heavy stars. So stars 100 to 200 times bigger than massive than our sun. So because these are so massive, the light was given out in ultraviolet mainly. So these ultraviolet rays, what they did is they ionized the neutral atoms again. So when they ionized, then all the light coming from these new stars, they started going away freely without getting absorbed. So this we call it as epoch of reionization, and the light from this time started moving away, and this is what exists even now. Okay, now from that we can see light. So this is called as epoch of reionization, and we expect that JWST we can see the light from these initial galaxies. So these are the very, very heavy stars, and these are only artistic view. Okay. Then proto galaxies. So proto galaxies, the initially formed galaxies, they were not very, very regular like whatever beautiful cylindrical structures, whatever you see now, but they were very, very irregular like this. Okay. So JWST is going to study these irregular galaxies also. Then life cycle of stars. If we are all aware of that, stars are born from gas and dust, then they undergo protostar stage, and if the fusion starts, there will be stars. And once the fusion ends, means once all the fuel gets exhausted, then the stars will expand to form red giant, and the central core will leaving out the core. So this red giant will undergo 3 types of explosions, leaving out. If the mass is less than 1.4 solar mass, which is Chandrasekhar limit, then it will become white dwarf. Or then after this white dwarf keep on giving out energy, and at one point it will become it will not be visible at all. It's called as black dwarf. Or it might happen that it might actually have more than this 1.4, then there will be nova explosion, leaving out a neutron star, or it might become black hole. This whatever the thrown out material is again used to form new galaxies, and the cycle repeats. So in Kannada we have Manninda Bandakaya Mannige. So this repeats. That's why it's called as life cycle. Okay. This JWST is going to study these star formation. Why can't we study that with Hubble? See, I told you that all these stars are formed in an area where there is a lot of gas and dust. This dust absorbs visible light. So we cannot see what is happening inside that. But the same picture, same place, field of view, taken with Hubble and taken with in infrared, you can clearly see that we can see much more details and many more stars getting born there. So in this way, we can see what is happening at the initial stage, that is the protostar stage. So that's why it is going to help us in understanding life cycle of stars. Okay. Then it's going to study the planets, known exoplanets. As of today, we have close to 5,000 exoplanets, that is planets beyond solar system. So this is going to study all those known exoplanets for biomarkers, means signature of life, whether the planets have water, planets have methane, whether the methane and planet, this one is in what stage, whether it is like water or ice or gas, how it is. So it is going to study, and at the same time it's going to study which one whether the life carbon dioxide is there and the other forms. Okay, it is going to start with the famous exoplanetary solar system called as TRAPPIST-1 system. It's first going to study with that. Okay, so coming to that JWST major life timeline, it was launched on Christmas Day. So it has reached somewhere here, where complete telescope commissioning is done, mirror alignment is going on. Okay, so then after that, the cooling will begin. So it will take 4 months for cooling, and then the first actual observations takes 6 months because the cooling, aligning all the mirrors and everything takes another 4 months. So we can expect the first images of that in somewhere around May, June. But don't worry, we already have first images. So this is the background is the first image taken from JWST, but you see that they are not properly aligned yet. It needs fine tuning. The fine tuning will keep on going for another some more time, and after that, we are sure it is going to throw many results which expected life, results which baffle us, or who knows, maybe somebody is looking back at us. Thank you. Akash?
Yes, sir.
No, I am done. Thank you.
Thank you. Thank you so much for this wonderful, lucid, insightful, and very explanatory talk. I hope all the participants have really gone through the system engineering aspects of making this kind of complex mission. I think more than 50 people have joined this session. They were very keenly listening to your talk, and there was no any single noise or issue.
Okay.
People were very attentive to the your talk, and we have few questions. People have already messaged. Now the floor is open to discussion. You may ask questions by unmuting yourself, or you can type your question in chat box. ನೀವು ಪ್ರಶ್ನೆಗಳನ್ನ ಕನ್ನಡದಲ್ಲೂ ಕೇಳಬಹುದು, ಕನ್ನಡದಲ್ಲೂ ಟೈಪ್ ಮಾಡಬಹುದು. ಸರಳವಾಗಿ, ತುಂಬ ಅದ್ಭುತವಾಗಿ, ಎಷ್ಟು ತುಂಬ ಒಂಥರ ಸುಲಲಿತ ಅಂತ ಹೇಳ್ತೀವಲ್ಲ ಸಂಗೀತದಲ್ಲಿ, ಹಾಗೆ ಸರಾಗವಾಗಿ ಒಂದು ಇಡೀ ಫ್ಲೋನ ಹೇಳ್ಕೊಂಡು ಬಂದರು ಸರ್. ಮತ್ತೊಮ್ಮೆ ನಮ್ಮ CPUSನ ಪರವಾಗಿ ಅವರಿಗೆ ಸದ್ಯಕ್ಕೆ ಧನ್ಯವಾದ ಹೇಳ್ತೀನಿ. ಈಗ ಪ್ರಶ್ನೋತ್ತರ ಸೆಷನ್ಗೆ ಹೋಗೋಣ. Let us take some questions which are already typed, sir. First one comes from Sakshi Hiramet from Raichur.
Excuse me, sir.
Yes, sir.
Sir, actually, I just have a point to raise. Like, there are some questions coming in Kannada right now, and I'm a person from Hyderabad who doesn't know Kannada. So, can you just translate the question and even answer the question in the English also?
Yeah. That is possible. We will do it.
Yes, sir. Thank you so much, sir.
Thank you, Subramanian. This is Kumari Sakshi Hiramet from Raichur. She is asking, is speed of light independent from frame of reference?
Yes. So that is one of the major reasons why we have all these things that is called as relativity. So whatever the reference of frame, the maximum speed is fixed at 3 lakh kilometers per second. Okay, I'm not putting 3.14 or something, but approximately 3 lakh kilometers per second in vacuum. This is the highest, and nothing can move faster than this.
Okay. Thank you. Hope Sakshi has got her answer. Mr. Vinay from Mistrak, he's asking, with the strength of the light decreasing due to inverse square law, how much of the light from 1.3 billion years ago reaches James Webb? Is the signal strength enough to be detected by James Webb?
Actually, since he said Mistrak, I'll just say that you may be aware of AstroSat. Okay, AstroSat has an instrument called UVIT on board, and UVIT is only 40 centimeters in aperture. So this has actually seen UV photons 9.2 billion light years away. Okay, this became a major news. You might be aware of this news. This is one of the major results from AstroSat. This scientist from Ayuka actually discovered this, and the person who discovered this was given Shanti Swarup Bhatnagar Prize just for this discovery. And when that 40 centimeter aperture telescope can see light from 9.2 billion years away, we are talking about 8.5. That is 4 is 16. It's only 16 square centimeters area, whereas we are talking about 36 meters square. So almost like 1,000 times better. And the second thing is, infrared will not get absorbed by dust and gas in the middle. So that means that the chances of seeing infrared is much, much more. Third one is, you know that if you see any spectrum, low energy photons will be much more dominant than high energy. It falls off usually. So in that way, we expect almost 1,000 times more photons in infrared than UV. So in all these things combining, we are sure that not just 1.3 billion years away, we are planning to see 13 billion years away, very close to Big Bang.
Yes, sir. He has mentioned as 13 billion years ago.
Okay, I missed it then.
I hope that has answered to Vinay's point. Then ಸುಬ್ಬಲಕ್ಷ್ಮಿ HK ಅವರು ತಮ್ಮ ಅಭಿಪ್ರಾಯವನ್ನು ತಿಳಿಸಿದ್ದಾರೆ. ಅತ್ಯಂತ ಸರಳವಾಗಿ ಗಹನವಾದ ವಿಷಯವನ್ನು ತಿಳಿಸಿದ ಶ್ರೀ ಗಿರೀಶ್ ರವರಿಗೆ ಧನ್ಯವಾದಗಳು. ಆಕಾಶ ವೀಕ್ಷಣೆಯ ಅನುಭವವಾಯಿತು ಅಂತ. ಸೊ
ಧನ್ಯವಾದಗಳು ಮೇಡಮ್.
Congratulations, sir. Subbulakshmi is telling he has explained the topic in a very simple and lucid way, and we felt like we went through stargazing during the course of this talk. This was her appreciation towards his talk. And one more, Dhanush RN is asking, what is dark energy and dark matter?
Okay, I'll tell you dark matter. So then I'll take it up dark energy. Now, you take any galaxy. Stars are going around the galaxy. For example, our sun is going around in the Milky Way center, our center of the galaxy. Now, so using Kepler's law, you can calculate the speed with which our sun is going around the galaxy, and you can calculate how much mass is required to move that. But if you see the galaxy, and if you see all the stars in the galaxy, and if you calculate their mass and sum it up, this is not even 20 to 30% of the total mass required for the sun to move with that speed. So now that clearly shows that there is something else which is actually making it move faster or slower, right? So what is that 70% which cannot be seen? So that is usually called as dark matter. Okay, dark energy is the one which to be frank, I do not have the complete understanding, but what I think is the one which is allowing these photons to move with an energy as we see today. Okay, I might be wrong with the dark energy, but dark matter is the one which is required but cannot be seen. We know that there is a possibility of seeing more mass, but only part of it we are seeing. Whatever is not seen is dark matter.
Okay, thank you. I hope Dhanush is satisfied with this answer. He can dig more. We have one more question from Sakshi. She is telling, can JWST detect gravitational waves, or it can only detect from infrared spectrum?
No, ma'am. It cannot detect gravitational waves. It can detect only infrared and very little of visible.
Okay. And Mr. Vinay has one more question. Sir, can James Webb image any of the exoplanets? Is there any technology in work to actually obtain good resolution images of exoplanets?
I do not know what is good resolution, but JWST is expected to image Jupiter-sized planets around small 2 to 3 solar mass stars using whatever I said, coronagraph method. So you remove the contribution of star and see only the contribution of the star planet, and from that it is planning to image it.
Okay, thank you. ಶ್ರೀಮತಿ BK ಹೇಮಾ ಅವರು ತಮ್ಮ ಅಭಿಪ್ರಾಯವನ್ನು ತಿಳಿಸಿದ್ದಾರೆ. ಅತ್ಯಂತ ಸರಳವಾಗಿ ಉಪಯುಕ್ತ ಮಾಹಿತಿ ನೀಡಿದ್ದೀರಿ. ಧನ್ಯವಾದಗಳು.
ಧನ್ಯವಾದಗಳು ಮೇಡಮ್.
Then one more abhipraya from Prashant. He says, although I joined late, I got the points on time machine very well explained.
Thank you, sir.
Congratulating you once again. Still, the floor is open. If anybody wants to unmute themselves and ask question directly to Dr. Girish, they can. ಯಾರಾದ್ರೂ ತಮ್ಮ ಪ್ರಶ್ನೆ ಇದ್ರೆ ನೇರವಾಗಿ ಅವರ ಹತ್ರನೇ ಕೇಳಬಹುದು.
ಗಿರೀಶ್ ಅವರೇ, ನಮಸ್ಕಾರ, ಹೆಸರು ದಿಲೀಪ್ ಅಂತ.
ನಮಸ್ಕಾರ ಸರ್.
ಅದ್ಭುತವಾಗಿತ್ತು ನಿಮ್ಮ
Just I have to intervene. So, Madam, Mr. Dr. Dilip is asking some questions. You can ask later, Madam. Next.
Sir,
Thank
I
you.
don't have a question. I have congratulations to you. It was excellent. You have explained multiple dimensions, James Webb Telescope, which are assumed to be known people. Like what is a telescope? Starting what is a star, on miles. Thank you.
Thank you, Dilip, for your encouraging words. Madam Shobha Devi, Madam, you can ask your question.
Okay, sir, good evening. And ತುಂಬಾ ಚೆನ್ನಾಗಿತ್ತು ನಿಮ್ಮ ಎಕ್ಸ್ಪ್ಲನೇಷನ್. ನಮ್ಮ ಒಂದು ಸ್ಟೂಡೆಂಟ್ಸ್ ಲೆವೆಲ್ ಅಲ್ಲಿ ಐ ಟೀಚ್ ಪ್ರೀ ಯೂನಿವರ್ಸಿಟಿ ಸ್ಟೂಡೆಂಟ್ಸ್ 9th 10th 11th 12th ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಗೆ ದೇ ಆರ್ ಅಬೌಟ್ ಟು ಬ್ರಿಂಗ್ ಅ ಬುಕ್ ಬೈ 2025 ಆಸ್ ಪರ್ NEP ನ್ಯಾಷನಲ್ ಎಜುಕೇಶನ್ ಪಾಲಿಸಿಯಲ್ಲಿ. ನಾನು ಅದಕ್ಕೆ ವರ್ಕ್ ಮಾಡ್ತಾ ಇರೋದ್ರಿಂದ ಇಸ್ರೋ ಸಿಲೆಬಸ್ ಹಾಕ್ಬೇಕು ಅಂತ ಚರ್ಚೆ ನಡೀತಾ ಇದೆ. ಈ ಮಕ್ಕಳ ವಯಸ್ಸಿಗೆ ತಕ್ಕನಾಗಿ ಈ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಅಲ್ಲಿ ನಿಮ್ಮ ಒಂದು ಕಾನ್ಸೆಪ್ಟ್, ಈಗ ನೀವು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ದು ಎಲ್ಲ ಇನ್ಫಾರ್ಮೇಶನ್ ನ ಪ್ಯಾರಲಲ್ ಆಗಿ ಅಟ್ಯಾಚ್ ಮಾಡೋದಾದ್ರೆ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಇನ್ ಬ್ರಿಂಗಿಂಗ್ ದ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಟುವರ್ಡ್ಸ್ ಡಿಜಿಟಲೈಸೇಷನ್ ಟು ಡಿಜಿಟಲ್ ಇಂಡಿಯಾ, ಅದಕ್ಕೆ ನೀವು ಪೂರಕವಾಗಿ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಗೆ ಸಪೋರ್ಟ್ ಮಾಡಿ ಆಡ್ ಮಾಡಿದ್ರೆ ಲ್ಯಾಬ್ ವಿಲ್ ಬಿ ದೇರ್ ಅಲಾಂಗ್ ವಿತ್ ದ ಟೆಕ್ಸ್ಟ್. ದೇ ವಿಲ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಬೆಟರ್ ಅಂಡ್ ಮೋರ್ ನಂಬರ್ ಆಫ್ ರಿಸರ್ಚ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ವಿಲ್ ಬಡ್. ಓಕೆ, ಅಲ್ಲಿ ಇಂಪ್ರೂವ್ ಆಗ್ತದೆ ಸೈನ್ಸ್ಗೆ ಸ್ಟ್ರೆಂತ್. ಕ್ಲಾಸ್ ರೂಮ್ ಅಲ್ಲೇ ಅವರು ರಿಸರ್ಚ್ಗೆ ಥಿಂಕಿಂಗ್ ಕೆಪಾಸಿಟಿನ ಇಂಪ್ರೂವ್ ಮಾಡ್ಕೊಳ್ತಾರೆ ಅಂತ ನನ್ನ ಅಭಿಪ್ರಾಯ. ಇದಕ್ಕೆ ನೀವು ಕೈ ಜೋಡಿಸ್ತೀರಿ ಅಂತ ನಾನು ಕೇಳ್ಕೊಳ್ತಾ ಇದ್ದೀನಿ. ಇದೊಂದು ಇನ್ಫಾರ್ಮೇಶನ್ ತಂದ್ರೆ ನಮ್ಮ ಸೈನ್ಸ್ಗೆ ಸ್ವಲ್ಪ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ವಿದ್ಯಾರ್ಥಿಗಳು ಬರುವ ಸಾಧ್ಯತೆ ಇರುತ್ತೆ. ಇದನ್ನ ಇಂಟರ್ನ್ಶಿಪ್ ಆಗು ಅವರಿಗೆ ಕೊಟ್ರೆ 9th 10th 11th 12th ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ವಿಲ್ ಬೆನಿಫಿಟ್ ಅ ಲಾಟ್ ಸರ್. ದಿಸ್ ಇಸ್ ಮೈ ಹಂಬಲ್ ರಿಕ್ವೆಸ್ಟ್.
ಮಾಡುವ ಮೇಡಮ್. KRVP ಮೂಲಕ ಕೆಲವನ್ನ ಆಲ್ರೆಡಿ ಮಾಡ್ತಾ ಇದೀವಿ. ಆದ್ರೆ ನೀವು ಹೇಳಿದ್ದು ಇಸ್ರೋ ಕೈ ಜೋಡಿಸೋದು, ನಾನು ಅದನ್ನ ಹೇಳೋಕ್ಕಾಗಲ್ಲ, ನಮ್ಮ ಮ್ಯಾನೇಜ್ಮೆಂಟ್ ಕಡೆಯಿಂದ ಬರಬೇಕು. ನೀವು ನಂತರ ನನಗೆ ಮೆಸೇಜ್ ಮಾಡಿದ್ರೆ ಇಲ್ಲ ಮಾಡಿದ್ರೆ ಸೆಕ್ರೆಟರಿ ಮತ್ತೆ ಚೇರ್ಮನ್ ಅವರ ಇಮೇಲ್ ID ಕೊಡ್ತಾರೆ. ನೀವು ಅವರು ಡೈರೆಕ್ಟ್ ಆಗಿ ನೀವು ಮೇಲ್ ಮಾಡಿದ್ರೆ ಅದು ನಮಗೆ ಬರುತ್ತೆ. ಓಕೆ, ಆದ್ರೆ ನಾವು ಡೈರೆಕ್ಟ್ ಆಗಿ ತಗೊಳಕ್ಕಾಗೋದಿಲ್ಲ, ಸಾರಿ, ರೆಡ್ ಟೇಪ್ ಕಾರಣದಿಂದಾಗಿ. ಆದ್ರೆ ನಿಮಗೆ ಕೆಲಸ ಆಗುತ್ತೆ. ನೀವು ಮಾಡ್ಬೇಕಾಗಿರೋದಿಲ್ಲ ಇಷ್ಟೇ, ನಿಮ್ಮ ಪ್ರಿನ್ಸಿಪಲ್ ಇಲ್ಲ ನೀವೇನೆ ನಿಮಗೆ ಏನ್ ಬೇಕಾಗಿದೆ ಅಂತ, ಏನ್ ಸಪೋರ್ಟ್ ಬೇಕಾಗಿದೆ ಅಂತ ಮೆನ್ಷನ್ ಮಾಡಿ. ಅವರು ಆಕಾಶ್ ಅವರು ನಿಮ್ಮ ಹತ್ರ ಇದೆಯಲ್ವಾ, ಚೇರ್ಮನ್ ಅಂಡ್ ರಿಜಿಸ್ಟರ್
ಇದೆ ಸರ್.
ಅವ್ರದ್ದು ಮತ್ತೆ ಸೈಂಟಿಫಿಕ್ ಸೆಕ್ರೆಟರಿ ಕೊಟ್ರೆ ನೀವು ಅವ್ರಿಬ್ಬರಿಗೆ ಬರೆದ್ರೆ ಸಾಕು, ಅಂದ್ರೆ ನಮಗ್ ಬರುತ್ತೆ, ನಾವು ಅಲ್ಲಿಂದ ಮುಂದೆ ತಗೋತೀವಿ ಮೇಡಮ್.
My request is let there be a reformation towards bringing the laboratory text reference manual books. ಬರೀ ನಾವು ಒಂದು ಮಾಡುವ ಕ್ರಮನ ಬರಿತೀವಿ ಹೊರತು ಇದುವರೆಗೂ ಅದಕ್ಕೆ ಅಟ್ಯಾಚ್ಮೆಂಟ್ಸ್ ಏನು ಮಾಡಿಲ್ಲ. Will let us attach these concepts, webinars ಎಲ್ಲ ಈಗ ಮಾಡ್ತಿಲ್ಲ.
ಒಂದ್ಸಲಿ ಅವರಿಂದ ಓಕೆ ಅಂತ ಬಂದ್ರೆ ನಾವು ಮುಂದೆ ತಗೋಬಹುದು ಮೇಡಮ್. ಅದು ಏನ್ ಬೇಕಾದ್ರೂ ಮಾಡುವ, ಬಟ್ ಆದ್ರೆ ಅಲ್ಲಿಂದ ಮೇಲಿಂದ ಬರ್ಬೇಕು.
ಓಕೆ, ಮೇಲಿಂದ ಬರಬೇಕು. ದಿಸ್ ಇಸ್ ಮೈ ಕಾನ್ಸೆಪ್ಟ್. ನೆಕ್ಸ್ಟ್ ಕ್ವಶನ್ ರಿಗಾರ್ಡಿಂಗ್ ದ ಟೆಕ್ನಾಲಜಿ. ಈಗ ಡ್ರೋನ್ ತುಂಬಾ ಮಕ್ಕಳಿಗೆ ತುಂಬಾ ತುಂಬಾ ಇಷ್ಟ ಆಗಿರುವಂತದ್ದು ಕ್ಯಾಮರಾದಲ್ಲಿ. ಈಗ ನಮ್ಮ ಒಂದು ಟೆಲಿಸ್ಕೋಪ್ ನು ಡ್ರೋನ್ ಕಂಬೈನ್ ಮಾಡಿದ್ರೆ ದೇ ಕ್ಯಾನ್ ಡೂ ವಂಡರ್ಸ್. ನೋ ಸರ್, ಇಸ್ ಇಟ್ ಪಾಸಿಬಲ್ ದ ಟೆಕ್ನಾಲಜಿ?
ಟೆಲಿಸ್ಕೋಪ್ ನಾನು ಹೇಳಿದ್ನಲ್ಲ ಮೇಡಮ್, ಟೆಲಿಸ್ಕೋಪ್ ನ ಡ್ರೋನ್ ಅಲ್ಲಿ ಕಳಿಸೋದ್ರಿಂದ ಡ್ರೋನ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಹೈಟ್ ಹೋಗೋದು 10 kilometers ಹೋಗ್ಬೋದು ಅಷ್ಟೇ.
Excuse me, sir. I have the same doubt. Can you just explain this in English?
Okay.
So a drone can travel the maximum altitude a drone can go is around a few kilometers, say 5 to 10 kilometers. But it won't help us in removing the atmospheric effect. So then going through drone will not help us in any way than observing the same from ground, right? At least on ground there will not be any like a shake, or it will be, you can put a maximum, there will not be limit on the weight. So there will be lot of benefits by not going through drone. Okay, so for astronomy I do not see any usefulness for drone And other than say solar eclipse are only solar eclipse is the only place where you can actually get something because you will be above the clouds, and so the chances of having continuous observation of a um, solar eclipse is maximum. Other than that, I personally do not see any use of drones for this particular purpose.
Okay, clear.
Because I'm looking at the anyway, the atmosphere will still be there.
Oh, thank you so much, sir. Thank you.
Thank you, ma'am.
Thank you, Shobha. Thank you, Dr. Girish sir. We have one more.
Excuse me, sir.
Yeah, Mr. Subramanian, please.
Sir, I'm right now I'm a student of Anurag University from Hyderabad. Yeah, so I just want a small request that I just want the recording of this meeting so that it will be helping me in my further any more works with the ISRO actually.
Yeah, Akash, you
Sir,
can
same
tell
here.
him.
Yeah, actually, this is not an official program being organized from ISRO. This is a event organized by Center for Public Understanding of Science. But even then, the recording is going on. We will share this webinar recording in our YouTube channel, and we will share you the link also.
Yes, sir. Thank you so much, sir. It was a great meeting and fantastic to learn many more new things. Thank you so much, sir.
You're welcome, Subramanian. Thanks for your patient time. One more question we have, sir, from Amog Rao. Sir, can we implement time mission on Earth?
When I said time machine, it's not that I can go back and become a small kid, or I can go back and see my dad and mom's marriage or something like that. I'm not talking about that kind of time machine. I'm just talking about life of stars and galaxies, etc. When they were young, how they look, when they were born, getting born, how they looked, etc., etc. So in that way, whatever you're talking about, setting up a time machine on Earth may not work.
Okay. We have one more question, sir. Sir, could you please explain briefly about the first selfie sent by JWST primary mirror?
First, what?
First image, first selfie sent by James Webb
Okay.
primary mirror.
Okay. So JWC has 18 mirror segments. Okay, hexagonal mirrors. I told you, no. So each one can be actually moved in particular angle. So one of them was made such that only have the light from the secondary falls on again back on that. So in that way, it was the picture was taken. That's how what is called as selfie.
Okay. Mr. Prakash Ji says, thank you, Dr. Girish, for giving insight on both Hubble and James Webb. Thanks to organizing team. So thank you so much for your encouraging words, Prakash. We have one more. Srinath says he is complimenting Mrs. Shobhaji for a good question from Shobhaji. Then Ms. Sangeeta is asking, thank you, sir, for providing an excellent presentation on Hubble and JWST. Thank you, Sangeeta. Pujita is asking a question. Is ISRO making an attempt to launch telescope like AstroSat?
Okay. Thank you, Pujita. So, see, AstroSat itself is from India only. It's India's first multi-wavelength observatory dedicated for astronomy. It is launched from ISRO. So, the success of AstroSat has prompted us to take up other science observatories. So, they are in various stages of development. For example, Aditya, which is going to study sun, is going to be launched sometime this year, and then followed by one small satellite which is going to study X-ray polarization measurements. So like that, we have plans for a UV telescope, maybe a one which can help us following up gravitational wave events. So like that, we have some 4 or 5 of them in various levels of development, but none of them are finalized yet.
I hope Pujita, you are convinced. Mr. Rajendra Kumar, he is asking, sir, how can we build a career in astrophysics after MSc Physics?
Okay, I think I can answer this because I also came after MSc, and I'm sure Srinath and many people came like that. So one of the ways is you can actually take up research as a career. You can actually join a PhD program. After a PhD program, you can take up a postdoctoral fellow and then continue as a professional researcher. That's one of the best ways after MSc.
Okay. Hope Rajendra Kumar has got answer to his question. Mr. Srinath says, thank you, Girish sir. What is the lifetime of JWST?
Okay. JWST lifetime expected to be 5 years, but see, when we are talking about any space mission, most of the time the life is actually defined by the amount of fuel left in the satellite, because you have to be moving it to target multiple objects and then to transfer the data, and for commands everything it has to move such that its antenna is towards Earth, etc., etc. So for all these things require fuel. So now this fuel is the one which defines the life of a satellite. It's like you have a car. So what is the assume that the car's life will end when it stops. When it will stop, when all its fuel is exhausted, unless and until you refill on the way. So, but these satellites cannot be refilled. Okay, so that means that once all the petrol is exhausted, then the car will stop. The car perfectly working, might be working, battery might be working, even your AC and audio, other things might be working, but because it do not have petrol, it cannot move, right? That's the end of the car. So similarly, here also, electronics and other things undergo so much of a rigorous testing, and that it will last for tens of years. Okay, but even everything is working. If you don't control it, then it is of no use. So the control and everything, the pointing, everything comes with the fuel. JWST, the launch and its orbit and its reaching up to L2 is so perfect that they have saved a lot of fuel. Whatever they have put it as a margin, all of them is actually saved, will be used for mission. So in that way, they are expecting that it will survive at least for 10 years and it will go for 20 years at a minimum, even though its design life is only 5 years.
Okay.
Hubble, for example, Hubble was also actually supposed to be for 5 to 10 years, but now it has completed 30 and going strong.
Okay, thank you, sir. I have a question, personal question. Sir, though the whole humanity is divided geographically, this is a collaborative project. Can you throw some more light on this, sir?
Oh, that's a very good question.
Because people should understand how science is made. So.
Yes, I'll say that even though it says that it is NASA's mission, okay, it was launched from Ariane space, that is from French Guyana, and some of the detectors, for example, that FGS was made by Canada, and other two of the systems came from Europe, and the heat shield, some of them came from other European countries. So India do not have much participation in this, but it is like a throughout the world endeavor, and the launch was actually managed by an Indian.
Okay. Thank you.
Thank you.
There are some questions related to how did you join ISRO? What is the way? Like such questions are there. Like you can answer it in a very briefly, sir. Lot of questions.
After my MSc, I joined Indian Institute of Science. I underwent in the entrance exam, and after interview, I got selected for the PhD. After my PhD, I joined Tata Institute of Fundamental Research for postdoctoral fellowship. When I was at Tata Institute of Fundamental Research, I got an offer to join ISRO. So I joined ISRO in 2008. So from then, this is my 13 years I have completed in ISRO.
Okay. I hope.
Initially, I worked on Rontagen 2. It is a collaborative effort between Russia and India to observe Sun. Okay, that was the first time I worked on a space system. So following that, I worked on. By the time I reached URSC, Chandrayaan was already in space. I worked on the radar data from Chandrayaan. Currently, I am managing everything of AstroSat, day-to-day activities of AstroSat, from mission planning to data delivery.
Okay, it's wonderful, sir. Prashant had some questions. You can ask, sir. Prashant.
Yes, sir. I have a question. Like, although it is a priceless for science, it is a multi-billion-dollar project, and multinations are involved in this. So, how you will define the cost involved in it, and how the India can take some notes of it, like in future also, if it want to maintain some costly projects like this.
I did not understand how do we take care of projects. So you mean to say that it $200 billion were spent
It's a
on
200 billion.
GWST?
Yeah, it's a very costly project. One thing it's a very costly project, and multinations are involved in it. So it's like a collaboration of multinations. So if in future India wants to project itself in such a sphere and lead in this position, can it do it? Is my question.
Okay. We are already doing that. On Chandrayaan, 6 payload experiments came from other places like NASA and ESA and even other places. Okay. So we already have these collaborations. So in AstroSat, 2 of the detectors, SXT and Soft X-ray telescope and UVIT, respectively. And in the Venus mission also, we are planning to get when it goes. So there are few proposals from outside India. Okay. And the UVIT, which what I just said, UV image, that UV telescope, which is going to go sometime later. So that is a collaboration between Canada and India. So it is going to be a 50-50. Like this, we do have such kind of collaboration with other parts of the world. So it's not that India is actually trying to do it everything on its own.
In fact, our space program
Thank you
is
for
a
your
collaborative effort. Prashant sir, if you look at the history of ISRO, the space initial INCOSPAR, all those efforts were collaborative efforts. So from the beginning, we have that point in our mind. Our founding fathers have kept that spirit since the beginning.
Yes, sir. Thank you very much.
Yes, sir.
Thank you.
I would like to say some more points.
Amog Rao has a question.
Amog.
Critical questions.
Yeah, sir, they tell that Mars once had water. Is it possible that if we had gone to Mars before and had implemented method that could have kept the water intact? Sir, what exactly is time? Could the method of implementation have settled on Mars? Say yes.
Okay, let me tell you. Whatever the method we are thinking of wouldn't have helped Mars for the reason that Mars do not have magnetic field cover like Earth has. So because Mars do not have magnetic field cover, charged particles will keep on bombarding the Mars, and it will be energizing the water, and the water will continuously. So there is no way we could have saved all the water. So forget about Mars. Let's actually save our own water on Earth now. See, you are all seeing that how the glaciers are melting and everything. We are losing water to the non-usable form. Okay. So if you are really interested, I would suggest that forget about Mars. Let's put our efforts to save water on Earth.
Yeah, that's the right way, right approach.
So his next question is interesting. I would like to take this question. Why couldn't we land in exoplanets which had signs of life even in technological era?
Yeah.
Okay. So Amog, let me tell you. As I mentioned, the nearest star, Sun, means other than Sun, is Proxima Centauri, which is around 4 light years away. Okay, that means that it will take 4 years for the light to move there. Now convert that into what is our space shuttle can do. See, as of today, Parker is the space shuttle which is moving the fastest. It is the fastest man-made object ever flown by humans. Okay, it will be moving at a speed of close to 100 plus kilometers per second. That means from here to Mysore, if I want to travel, I will reach there in 1 second. But even at this speed, if somebody wants to go to the nearest star, Alpha Centauri, Proxima Centauri, it will take around 20 to 30,000 years for them. What is our lifetime? 60 years? 100 years? The highest is around 150 years, right? So, how many generations are needed just to travel from here to there? So, unless and until we come up with a technology, like a significant technology change where that time travel means the speed is increased 100 to 1,000 times more, it is not possible for us to go anywhere near. Okay, that's why it's not possible to go beyond our solar system. That also, you know that there are two satellites called Galileo, which were launched by America. One of them was launched almost 40 years back. That has just left solar system. So it took 40 years just to cross solar system. Imagine how much time it is going to take to reach any nearby star. So whatever the technology we have, it's not possible to go to exoplanets as of today. Maybe tomorrow. I don't know.
I hope Amograv is convinced about his questions and answers given by Dr. Girish. Mr. Vikas D, he is asking, sir, does the black hole send absorbed objects outside a white hole? If not, according to research, what happens to the objects absorbed by the black hole?
Okay. If I put it all, thank you, Vikas. Jokes apart, we do not know what happens once the light or anything crosses event horizon, because as you know that black holes do not emit anything back, so they will even absorb light inside, so no information can come out of this one. Whatever we have is only theory, and whatever we can say is stories. So scientists are not sure what might happen once the matter or anything crosses event horizon.
Thank you, sir. Vinay Kumar is asking, sir, what is your view on intelligent life elsewhere in the galaxy, knowing that there are more than 100 billion stars in our galaxy itself?
I told you that, so I do not see any reason why there should not be any intelligent life outside. But then there is a problem now. So now, unless and until they are technologically advanced, much more advanced than anything what we have achieved, there are only two possibilities. So assume that they have got intelligence around the same time as us or later than us. Okay, so even if they got intelligence same time as us, so for them to reach us, as I just mentioned, unless and until the technology is completely different from our technology, it takes thousands of years. And modern science started only a few hundred years back. We haven't even crossed 1,000 years. So where we are talking about intelligence which has to be evolved at least 20,000 years back. So they might not want to contact us, because for them we are like cockroaches. Those people whose intelligence started little late, they have not reached to the level where they can contact us. So in that way, we don't know whether there is intelligence life outside, and if it is there, whether they don't want to contact us, or they don't want to be seen by us. So in whatever our efforts, we have not come across any intelligent life as of today. But that do not rule out intelligence life outside. Okay, it's just like some time back I was reading some book. They mentioned that, so you go to a ocean to play, and you take 1 spoon of water in your hand and say that since this water do not have any fish, I think that there is no fish in this sea. Can you say that? So whatever we can see, whatever we can study, whatever we can see is only that spoon. we don't know what is there in the entire sea.
I hope it has answered Vinay's question. Mr. Anish Sagar Naidu is asking, sir, how can nanotechnology be used in space research? If yes, how it will be useful?
One of the major strengths of nanotechnology is its strength per unit mass. So by actually using its strength and other things, which is reduces the mass. So nanotechnology is used some places where we want to reduce the weight while maintaining the strength. So those places it is under utilization. But most of the rocket you may be aware of is fuel. So unless and until nanotechnology helps us in actually converting that into something else, I don't see much use of nanotechnology in rockets.
Okay, thank you. Ms. Vinay Kumar is telling, thank you, Girish sir, for the insightful answers.
Thank you.
Sir, how many more minutes you have, sir, to take questions? I think...
I don't mind. My kids are not here, so I can take more.
So, those who are asking questions are many more kids around, and good to have, in fact. But it is time up already. 2 hours we are running now. In case
one more interesting point you can make, sir, Chennai sir, regarding the evolution. Even if we go back in time, and if evolution starts again, it may not reach the stage where we are now. So,
yeah, exactly. Evolution cannot be reproduced. See, if you go back and start evolution again, we are not sure that it can happen the same what we are now. So that way,
fluke. It's just a fluke thing.
We do not know whether the intelligence can happen the same way.
Exactly, sir. Exactly. So, sorry for this example. It do not mean that Sachin Tendulkar, if he goes back and if he gets reborn, he'll become another Sachin Tendulkar. Because things totally. which has to fall in place is very, very high.
Yeah, sometime back what happened was, there are beliefs that life can be silicon based, like we are all organic, carbon based.
Yes.
So the carbon can be replaced with silicon, which is again a tetravalent. So there are thoughts like that, but exactly that does it happen? We really don't know. As of now, the results are saying that no, it cannot be happened. But still, there are such doubts. If the silicon is functioning, or it can function like carbon, but does it happening the same way on Earth? No, it is not happening. We have nowhere silicon is, but only in parts of some paleontological issues wherein silicon has replaced with carbon. Carbon is, so that is different. But however, such doubts are just like stories.
So, for example, you might have heard of this water bear or something which was seen almost 7 kilometers deeper near volcanic activity inside the sea. So nobody expected anything to survive that kind of harsh environment. Very, very acidic because of the sulfur, and very, very hot. The pressure is so high. But there are multicellular organisms found there. So we really don't know what is happening on our Earth itself.
Yeah. So there is a deep hot biosphere. There is a concept called deep hot biosphere by name Thomas Gold, who argues that all our the so-called the carbon fuel that is continuously producing. So there is, that's a different argument. But however, the proofs are yet to have in a way.
Yes, sir.
Okay, the reason why.
If I may my comment. So the reason why astronomers are looking for carbon-based organisms even outside our solar system is, carbon-based, whatever we are trying to search for is carbon-based life form. So we know what are the biosignatures from the carbon-based. Even with that, we are unable to see life outside. So think about something which is completely not known to us. So we will not, even if we see, we will not know whether how to make out of it, whether it's life or not. So that's why we are concentrating mainly on carbon-based life form. It's not that we are not expecting any non-carbon based for life form, but we will not know how to recognize them.
Yes, yes.
Sir, we will take one last question before proceeding further. Srinath is asking, can we expect JWST strengthens the opinion of Professor Asimov's many-dimensional space-time concept? So you have to explain what is many-dimensional space-time concept.
No, I do not think JWST can do that. See, JWST, one of the main thing is to actually look at the cosmology as expected from Big Bang. Okay, I don't know what is multi-dimensional space-time concept. So according to them, if space travel is, Srinath, are you talking about space travel and others? I'm not sure. JWST may not help in that way.
I just draw to my attention to Srinath. I just remember a book by, I have forgotten the title of the, I remember the title of course, but I've forgotten the author. There is a book called Fifth Dimension, and that is physics and fifth dimension. I just vaguely remember the title. Of course, it talks about the concepts of all other dimensions put together and how do they work. I don't know the reality of those things, but multidimensional in what concept, in what context Asimov has turned out, I really doubtful in a way. But
we are aware of only 4 dimensions physically.
Yeah.
So others are
but there is a
only
book,
in the
Physics
mathematics.
and its fifth dimension. There is a book.
Others are in mathematical realm only, as of now.
Correct. Yeah.
I think all good things and deeds should come to an end. I hope with this we can conclude this webinar. So I now request Professor Venkatesh Ji to propose vote of thanks, and before that to summarize the proceedings of the today. Over to you, Professor Venkatesh sir.
Good evening everybody. Namaskara. Today we come across with the webinar on James Webb Space Telescope by Dr. Girish. It has started with the introduction by Dr. Chandish and comparing with MC with Akash. It is seen that the webinar started with a simple question: how many stars we can see from our naked eyes? It started with 2,500 and it ended with billions. Okay, so really it is amazing to see that billions of stars with our eyes with the help of these telescopes. Okay, the webinar is unfolded. The technology, the marvels behind James Webb Telescope, the webinar is unfolded very smoothly. The credit goes to Dr. Girish for his simple way and explaining the heavy technology, high technology in simple words. So at the same time, I am very much appreciated and very much overwhelmed with the way he has answered, taken the questions. The presentation part is one. Second part is the intelligent questions have come. At the same time, insightful answers have come from Dr. Girish. So, lot of things, you have gone inside to the science, basic science. So, you started with the galaxies and you went to the nebulas and you went to the star formations, and we discussed about the dark matter, discussed about the dark energy, then black holes. So, the lot of science, the basic physics, as well as the chemistry, everything has come in. Finally, we come across the biology part, the carbon. Okay. So the unfolding of this science, basic science with high technology is very amazing, sir. Very thankful to you, sir, Dr. Girish, for accepting our invitation. And I am very thankful to Mr. Srinath for helping us in organizing this workshop. Thank you, Srinath. And I am thankful to Shankar sir for providing this one webinar site, that is WebEx, for us for CPUS, and he's helping us with this technology. And I am thankful to Shankar sir. And We are very much thankful for the guidance given by Dr. Channesh, Director CPUS, and Akash. You are wonderful in organizing and carrying out this webinar in all respects and handling the questions and a total MC in term. And I am thankful to all the students, especially the outstation students. This time we got the students from Anurag University, Mr. Subramaniam from Hyderabad, and Mr. Anish Sagar, Mr. Amog. Wonderful questions we have got from them, and Shobha Madam, and even Vinay from ISRO. So all questions are intelligently managed. So the insight what Girish has given as some good questions have come up such that every participant has got insights into the science and as well as the technology behind James Webb Space Telescope. Overall, it is a wonderful program for us. We learned from each other, and it's a learning, unlearning, and learning process has happened. New knowledge has come up with us, and thank you very much. Thank you one and all for this. At the same time, Nadagoda DD from URSC is also present over here. For his present, we are very much thankful. And once again, I am extending my sincere thanks to each and everybody who has participated and actively who has involved and who has given us a very good encouragement for organizing such a workshop, such a very webinars. Thank you one and all. Well, Akash, over to you.
Thank you so very much. It was a fantastic galactic tour that we went into.
Thank you, Soumya Madam.